This section introduces frame relay principles in support of maintaining existing legacy technologies within the enterprise. The introduction of frame relay during the 1990s saw a rapid growth in its implementation and adoption by many enterprise businesses. Over time, however, newer carrier-based solutions, such as multi-protocol label switching or MPLS, have been introduced, allowing for greater advanced service opportunities to be offered by providers. And so frame relay networks continue to be maintained for existing customers as the technology is slowly phased out. Frame relay is primarily a service provider technology. However, enterprise administration requires that engineers are capable of establishing connectivity over frame relay virtual circuits at the edge of the enterprise network, as well as be familiar with the circuit establishment process to identify and resolve issues that may occur. So upon completion of this section, it is generally expected that trainees will be able to describe the function of the DLCI in a frame relay network, describe the LMI negotiation process, as well as configure frame relay using both static and dynamic mapping. Frame relay represents one of a number of legacy technologies like ATM that rely on serial-based connections to establish primarily WAN-based networks that are able to support peering between remote locations such as branch offices. Frame relay was developed based on the older X.25 protocol and was designed to simplify many of the processes that effectively reduce processing time and focus its operations to only the physical and data link layers. Legacy forms of technology, however, are slowly being phased out in favor of IP-based technologies, and so we find many of the networks today may not include frame relay, instead establishing connectivity at the enterprise network edge over technologies such as MPLS. For existing frame relay networks, however, we demonstrate the principles and configuration necessary to maintain and support their operation. Being a serial-based technology, the reliance on synchronization is still required, and as we see here, the mechanism for synchronous serial signaling are implemented in the form of DTE and DCE-based devices, with the DCE providing the clocking mechanism for the link. An engineer's primary focus for the enterprise is to support the link between the customer network edge and the provider edge of the service provider's network. The inner workings of the ISP frame relay network are as such outside the scope of the requirement for supporting the enterprise network. The path over the frame relay network is determined by virtual circuits, each of which is represented in frame relay by a data link circuit identifier or DLCI. These virtual circuits are considered to be locally significant, meaning that in order to reach an intended destination, the sender need only associate the local DLCI with the intended destination address, and therefore is not required to learn the DLCI of the remote peer. The DLCI can be any value from 16 to 1006, where other DLCI are reserved. There are in fact two forms of virtual circuit that may exist, the first being the permanent virtual circuit or PVC, that is basically a logical mapping of the circuit from end to end. The other is the switched virtual circuit or SVC, that builds the circuit for each connection each time a connection is to be made. But within frame relay, this form of virtual circuit is rarely applied. In order to validate the state of a virtual circuit, we must firstly ensure that the signal between the edge device and the frame relay switch with which we are peering is operating correctly. The means by which this is performed is through the local management interface, or LMI for short. The LMI will generate status inquiry messages that initially originate from the DTE and are received by the DCE device. The DCE device will then respond to the received status inquiry message. As a result, the DTE device is able to determine the current status of the link and PVC, where we will find, if all is well, that the link status is typically set as up and the PVC status as active. Once the LMI is successfully negotiated, it is then necessary for the local DTE device to bind the local circuit identifier, or DLCI, to the destination address at the end of the virtual circuit. There are two ways that this can be done, either manually or dynamically. Where it is dynamically performed, we will find that an adaptation of the ARP protocol is used, known as inverse ARP. What this basically does is takes the IP address of the remote device, which in this example is 10.1.1.2 of RTB, and binds this address to the relevant local DLCI that represents the circuit that is used to reach the destination. We can simplify this concept by comparing it to getting on a bus. We typically know the bus number and the destination of the bus since it is usually written on the front of the bus. But as a passenger, we don't necessarily know the route that the bus will take to get there, only that it will eventually get there. In the same manner, only the service provider is aware of the actual route of a virtual circuit through the frame relay network. As such, our concern is only to connect to that circuit. Inverse ARP will generally do the hard work by generating a request to discover for a locally known DLCI number the destination address at the end of the circuit, to which a reply will be sent containing the associated address of 10.1.1.2. RTA will then be able to generate a binding table entry that associates the destination of 10.1.1.2 with DLCI 100, allowing RTA to understand that any traffic destined for 10.1.1.2 should be pushed over the virtual circuit associated with DLCI 100. If we recall from the section covering RIP routing, split horizon was used as a means to prevent routes that were learned on one interface from being advertised back over that same interface, in order to prevent routes from being falsely learned. One of the problems faced when supporting frame relay networks is that such networks may often take on the form of a hub and spoke topology, in which traffic must traverse the hub device before traffic is able to reach the spoke devices. In the example shown here, we can understand that a circuit exists between RTB and RTC via RTA. RTA, however, only has a single physical link to the frame relay network in the form of interface serial 1/0/0. However, the circuit behavior means that traffic must both be received and forwarded over the same link. If routes are also shared and frame relay is enabled, the routes received from RTB and RTA will not be propagated to RTC as a result of the split horizon rule, which leaves us caught in a situation of whether to restrict the routes or risk routing loops over the circuit. The common solution for frame relay is to implement logical subinterfaces to resolve the difficulties of split horizon. Each device is associated with a logical interface that allows the split horizon problem to be circumvented and routes to be advertised without risk of routing loops occurring. This may be supported one of two ways, either using point-to-point subinterfaces that associate a single pair of peering devices with the same subnet, and as such establishes a single virtual circuit. This effectively simplifies the determination of the virtual circuit to use, since any routes associated with this subnet will only be forwarded over this point-to-point virtual circuit. The other form is point-to-multipoint, that allows each sub-interface to be associated with multiple virtual circuits that again belong to the same subnet. In this case, because there are multiple virtual circuits for the same subnet, mapping through static configuration or inverse ARP is necessary to determine the correct virtual circuit to use to reach the destination. We now take a look at how frame relay is configured on the enterprise edge router in order to establish a virtual circuit over the service provider-based frame relay network. Typically, the virtual circuit is defined by the service provider that will be responsible for determining the DLCI that the DTE device should use at the enterprise edge. We should begin, however, by establishing the link layer protocol type to be frame relay, in the same manner as performed for the HDLC and PPP link layer encapsulation, by using the link protocol command under the serial interface view. After being prompted for confirmation of the change, it is also necessary to set the frame relay interface type to DTE. Since we are wishing to establish dynamic mapping using inverse ARP, we must also apply the FR inARP command. We can confirm the parameters set using the display FR PVC info command that allows us to determine the current status of the virtual circuit that has been established between RTA in this case and the peering frame relay switch. We can see with respect to serial interface 1/0/0 that the interface is associated with DLCI 100 is physically active and has been learned from the DCE side as a result of the usage parameters showing as unused. Inverse ARP can also be clearly seen as active, as has been highlighted in the command output. For discovery of the remote address with which the local DLCI is associated, we are able to use the display frmap info command that basically displays this mapping. From this, we can see that where the DLCI is 100, the remote address is 10.1.1.2 and has been learned via inverse ARP over interface serial 1/0/0 in this case. The broadcast entry here represents that any routes learned by RTA can also be carried over the frame relay network and advertised to peering devices on the other end of the circuit. We find also that the status is currently active, which shows the virtual circuit as operational. If, however, the status is found to be inactive, the current configuration parameters between the DTE and DCE should be checked. We are able to alternatively perform static mapping of any frame relay virtual circuits. As with the dynamic mapping, the same parameters for establishing the link layer protocol as frame relay and the establishment of the interface type on the local router as DTE should be performed. We find, however, in this instance that any active frame relay inverse ARP command is disabled to prevent dynamic discovery of the remote peer address, and instead allow the static mapping of the remote address to the local DLCI to be performed. We see this being performed here using the frmap_ip command, which is followed by the remote IP address and the local DLCI number to which this IP address is binding. If we wish to allow routes to be advertised over the frame relay network, we may also wish to include the broadcast parameter here. However, this is optional but generally recommended. In this case, however, we show the result of using the frame relay map command without the broadcast parameter, since there are no routes to advertise. We can again return to the use of the display frpvc info command to view the results of configuring the DTE device with the static configuration. As a result, we generally find that the DLCI is again recognized as 100. However, we now find that the usage is shown as local, which informs us that the virtual circuit has been learned locally as a result of the frame relay mapping configured. We also find that the inverse ARP is now disabled, effectively preventing dynamic mapping from being performed. For the end-to-end connection, we find that again the DLCI and bound IP address are listed. However, it is no longer associated with the inverse ARP since it was statically mapped. The general result, however, means that 10.1.1.2 can be reached. Since we did not include the broadcast parameter in this instance, we find that it is no longer listed in the display output for the frame relay map info, and so routes learned by RTA will not be carried to the remote device. We then come to the summary for this section, and we just have a couple of questions here. The first asks, if the PVC status is set as inactive, what action should be taken? Well, there are a number of possible reasons why the PVC status may show as inactive, and so a step-by-step approach must be taken, beginning with the physical interfaces, followed by the local link, and finally the end-to-end mapping. If the interface is confirmed to be physically active, we should determine whether the LMI is able to send and receive status messages over the link. We can do this using the command display fr LMI info. If status messages are being received, we shall observe the output of the display frpvc info command to verify that the PVC is active and that the binding has been performed between the local router and the peering switch. If this is active, we can finally check the mapping using the display frmap info command to determine whether the end-to-end mapping has been established. What is the purpose of the inverse ARP in frame relay? Well, the inverse ARP is used to allow a virtual circuit associated with the local DLCI to dynamically learn of the remote address and create a binding between the two parameters and store the binding in a mapping table. Packets intended for the destination IP listed in the mapping table will be able to determine the relevant virtual circuit that should be used to reach the destination based on the DLCI.